5.1 and 5.2 culminate into section 5.3, the definite integral. And here's the definition of a definite integral. We're going to let f of x be a function defined on a closed interval. We say that a number j is the definite integral of f over the interval from a to b, and that j is the limit of the Riemann sums, and this is the formula for the Riemann sums. I'm not going to make you memorize this or do anything with it, as a matter of fact. We just kind of hit the highlights in 5.2 of what a Riemann sum is. So this is the limit of the Riemann sums if the following condition is satisfied. Given any number epsilon greater than 0, there's a corresponding delta greater than 0, such that for every partition of that interval, with the norm of the partition, which is the distance being less than delta, and any other choice of number in that partition, we have the sum minus the limit is going to be less than epsilon. This is the delta epsilon definition of an integral. Just like we had the delta epsilon definition of a derivative that we kind of looked at and then never looked at again, because we learned all the shortcuts for taking derivatives. This is the delta epsilon definition of the integral that we're never going to look at again, because we're just going to start taking integrals. And remember, last time we got these symbols here. This symbol right here is an integral sign. It is not an S. It's more like a line with a little hook at the top and at the bottom. Kind of S-shaped, S-like, but it is not an S. Please don't draw it as an S. Okay? A we call our lower bound. A is the lower bound on this interval up here. Remember? And then B would be your upper bound over the interval. F of x is the function that's part of the integrand. The integrand is what you're integrating. Just getting the vocabulary down. You need to become familiar with the vocabulary. This dx tells you your variable of integration. You say, well, if x is the only variable in the function, don't we know we're taking the derivative with respect to x? When we do baby integrals, yes. When you get into Cal 3, you're going to be doing multiple integration of equations that have 2 or 3 variables. And you'll have a dx, dy, dz. And that tells you the order that you want to take the integral of each variable. So there's bigger things coming up. You just need to know what this is. This tells you the variable that you're taking the integral with respect to. And this is said to be the integral from a to b. When you find this value right here, you've evaluated the integral. And it's going to be the area under the curve of f. You know, let me write that down because I don't think that that's painfully clear in this section. This gives you the area under the curve of f. So let's say that we had a function, and I'm going to, just for easy's sake, make it positive. Let's say that we have a function that looks like this. And I wanted to find the area from A to B. Well, once I find this integral of this function, f of x, I've found the area from A to B. So we're looking at this area right here. And we would say that that area is equal to the integral from A to B of f of x dx. That's what an integral represents. Yes, lower bound on bottom, upper bound on top. And we're going to get some rules, I don't know if it's in this section or not, about what happens if you switch the order of the bounds and all this stuff. Okay?
So the lower bound is just always the first point to
It's the point farthest to the left where you want to start finding the area, and B is always the point farthest to the right. Got my left and right backwards, but you get the idea.
Yeah.
All right. Theorem 1, the integrability of continuous functions. If a function f is continuous over a closed interval, or if f has at most finitely many jump discontinuities there, then the definite integral from a to b exists, and f is integrable over a to b. Integrable just means the derivative exists. Okay? Continuous functions are integrable. Or if you have just a jump discontinuity, you can still find it. If it goes off to infinity and that's why you have a discontinuity, the function is not integrable. Okay? All right, theorem 2 says when f and g are integrable over an interval from a to b, the definite integral satisfies these rules. These are the rules of integration that you are going to have to memorize. Yikes, didn't want to do that. Hang on. I want to make this. This is table 5.4 in your book. I'm not sure what page it's on. What page? 317? Huh? Let's talk about them so that they'll be easier to memorize, okay? The order of integration. Look what happens here. You had mentioned the bounds. If we switch the a and the b, what we have is the opposite value. If you switch your bounds, you have a negative value, okay? So let's make a note of that. If you switch the bounds, well, that's kind of what one says. Oh, yeah. Okay. Number 2, zero width of an integral. If your upper bound and your lower bound are the same, what that means is you're trying to find the area of a line, and that just doesn't work well. Okay, so here's your function, and here's the point A, and if you're looking at the integral from A to A, that's the area of a line, and lines don't have area, lines have length, right? So if the bounds are the same on your upper bound and your lower bound, you have a zero area. Okay? And these kind of make sense. The reason this one works is because if we went, on number 1, if we went from A to B and we switch the order, we end up with a negative length, right? So that's why when you switch your bounds, you get a negative area. You get a negative value of the integral. Okay? Number 3, the constant multiple. If you multiply a function by a constant, that's like a scalar multiple, you can pull that constant out of the integral and multiply the integral by that same constant that's inside the function. Okay?
Multiply k times f of x.
If you have k times f of x, the integral of k times f of x, that's going to be the same thing as k times the integral of f of x. Okay? Sum and difference. You can distribute integration across addition and subtraction because remember, an integral represents an area. You can add and subtract areas. That's worked the same with limits, right? And derivatives. We distributed derivatives and limits across addition and subtraction. Same thing's true for integration. So that's not that big of a stretch for us even. Derivatives, if we had a derivative of a constant times a function of x, couldn't we take the constant times the derivative of the function of x? It works the same with integrals. So all the rules that you know that apply to derivatives will also apply to integrals. So when you say, oh, I got to memorize a whole bunch more stuff, not really. Not if you knew it to begin with. Well, that's the key. All right, additivity. If you add, look at this. And let me draw a picture, I think, to help. Oh, hey, we have nice pictures here. Why am I drawing? I forgot about this. I made these lecture notes out last week. I'm sorry. And their pictures are prettier than mine. All right. The additivity one. It says that if you have a function, oh, by the way, this picture goes with number 2. This picture goes with number 3. This picture goes with number 4. Number 5 is additivity. I'm guessing that's this one. Yeah. If you have a function and this you want to integrate from a to b, your function, and you also want to add to it the integral from b to c, that's the same thing as the integral from a to c because it's a continuous domain there. You haven't broken up your interval. So the integral from a to b plus b to c is going to be the integral from a to c. Does that make sense? Visibly. Number 6, max and min. It says if f has a maximum value, if f has maximum value, max f, and minimum value, min f on the integral, then min f times b minus a is less than min f times, yeah, I don't know that I've used that one ever, but hey, it's there, and we have a picture. And 7 is domination. If one function has a greater value than another function, then that area of the larger function will always be greater than the area of the smaller function. Yes, it is. And now we can use these properties to answer some questions. I will ask questions in this form on your next test, so be prepared. I've said that before and it didn't make a whole lot of difference, but hopefully it'll make difference now. The functions f and g are integrable. You're told that, so you believe it. And the function f from 2 to 4 has an integral value of 5. The function f from 2 to 7 has an integrable value of 3. And the function g from 2 to 7 has an integrable value of negative 3. Yes, integrals can be negative. They can have negative values. Okay? So what we're asked to find then, or actually we're asked to apply the properties we just learned. What would be the value of the integral of f of x from 4 to 4? 0. Because our lower bound and our upper bound are the same. That's looking back here at this picture number 2. Right? We're talking about the area of a line. That doesn't make sense. Let's go over here. The integral from 7 to 2 of g of x. What did we do here? It's going to be positive 3 because it's the opposite of what we got. We switched our bounds. Because the integral of g of x from 2 to 7 was negative 3, the opposite of that is positive 3. See how it works? We're just using the rules. All right. We have the integral from 2 to 7 of 8 times g of x. Well, that's going to be equal to 8 times the integral from 2 to 7 of g of x. So that's going to be 8 times, and that is, okay? Here we have the integral from 4 to 7 of f of x dx. That's equal to the integral from 2 to 7 of f of x dx minus the integral from 2 to 4 of f of x dx, isn't it? Because you go from 2 to 7 and you take away from 2 to 4. Let me draw a picture. Hang on. Here's 2, 3, 4, 5, 6, 7. This integral, the area from 2 to 7, we said up here was going to be 3. So from 2 to 7, we get the area as 3. And if you take away the area from 2 to 4, hang on, I need more space. Give me a sec. So this is going to be 7. Hang on. Let me do this. hang on, you're looking at the x values here. So this we said is 4. I know this goes all the way from 2 to 7. And then I'm going to take away the area from 2 to 4. And if I take that away, what am I left with? I'm left with the area from 4 to 7. So when I take away that area from 2 to 4, we were told that that was 5 minus 5. We're going to get -1. Huh? 2 to 7 was 3. Ah, okay. So we have 3 minus 5, and we end up with -2. Okay? We're just going back to these values up here. We were told, but do you see how I knew that I needed to subtract? Let's go back to this problem right here. If your domain is continuous here, if I wanted to know what was, let's say I wasn't told this area right here. Well, then it would, but I was told the area from A to C. If I was told the area from A to C, I could subtract off the area from B to C, and then what would be left over is that. It's the same thing that's going on. I was told the area from 2 to 7 right here, and I wanted to take away the area from 2 to 4, and then what was left was the area from 4 to 7. Does that make sense now? Okay. All right, the next problem, we have the area from 2 to 7 of g of x minus f of x. Well, we said that integration distributes across addition and subtraction. So this is going to be equal to the integral from 2 to 7 of g of x dx minus the integral from 2 to 7 of, and what did we say this was? -3 minus, and then for the f of x, 3, -6. Okay? On this one?
Yeah.
Okay.
You got 3 minus 5, 2.
Because the integral from 2 to 7 of f of x dx was equal to 3.
Did you have 4 to 2 up top also?
From 2 to 4, right here.
From 2 to 4? Okay, I didn't see it.
Yeah, you needed that. Okay, all good? All right, what are we going to do here? This is equal to what? 3 times the integral g of x dx. Only the g is being multiplied by the 3. The f isn't, because that 3 is not outside the brackets. So this is minus the integral from 2 to 7 f of x dx. So this is going to be 3 times what? -3 minus 3. So that's going to be negative 12. Is that right? Okay. Just applying the rules. Any questions? Do you like this or not? It's fairly straightforward, I think. All right. And I've been telling you this long before, but now officially the book is telling us the area under the curve over a closed interval is this integral. Well, I've been telling you that. I gave away that back in 5.1, I think. So my big ta-da is ta-done. So we're asked to graph the integrand here. What's the integrand on this integral? Y equals x plus 6. And use the area to evaluate the definite integral from -4 to 6. So what I need to do is I need to get a grid up here to sketch in the graph. So we start with, by the way, what type of equation will this be? Y equals x plus 6. Linear. So we're going from -4 to 6.
So what if it was f of x? Would you just say x?
3. No. 1, 2. Hang on. 3, 4, 5, 6. All right. When x is -4, y is +2. So we have a point at -4, 2. Oops. 1, 2. And when x is 6, y is 6. 4, 6, 8, 10, 12. I'm going to let each of the y-axes be 2 points because otherwise I run out of space. Here's -4, there's 5, and 6. Alright, so we're going to graph this function y equals x plus 6. That's a linear function. It has a y-intercept at 6. And it goes through this point all the way up to this point. So here's the point 6, 12, and the point -4, 2. And what we want to do is we want to find the area between here, right? What geometric shape is this? No, it's not a triangle. It's a trapezoid. Because I have 2 parallel sides. See, this is a trapezoid. And what is the area of a trapezoid? 1/2 base 1 plus base 2 times the height. Base 1 is the length of base 1. That's going to be this distance right here. What is that distance? 2. The y values are the height. So we have, looking at the picture then, we know that this area is going to be equal to 1/2 times the first base is 2, the second base is this line right here, and that's going to be 12. And then the height is this distance along the x-axis, because remember the height has to be perpendicular to the bases. And that height is going to be from -4 to 6. The length of that 6 minus a -4. So we end up with the area is equal to 2 and 12 is 14. Half of that is 7 times 10 is 70. So we end up with the integral from -4 to 6 of x plus 6 dx equals 70. And we use the concept of area to evaluate this, right? Here's a formula for an average value. If you take that area and you divide it by 1 over the distance from B to A, here this would be 1/10, it would give you an average value. And that's going to come up, I believe, in the next section when we look at the mean value theorem. So for all intents and purposes, we're done with this. Now, we were able to evaluate this integral, this definite integral, because we knew a geometric formula. That's not always going to work, is it? All right, the next section we'll figure out how to handle an area when it's not a nice geometric formula, using the fundamental theorem of calculus, just so you know that something better's coming.